So let's take a look. So this one, how are you guys graphing that? I know how I did it. How'd you do it? Like this? This is how, who did it this way? Okay, so you notice we put a 0 in for x. What comes out for y? 1. Regardless of what this number right here is, this common factor we call it, it's going to be 1 no matter what, right? In a case like this. So if I put a 9 here or a 50 here or any number here, it's going to be a 1, isn't it? So right here. And then if we put a 1 in, 2 to the first power is 2, and if we put a 2 in, 2 to the second power is 4, and if we put a 3 in, 2 to the third power is 8, and I think I put, yeah, so, oh, did I put that in the right place? Should be right here. I got it a little bit off. There we go. And then, what about the other way? So if I put a -1 in, so we need to think about, make sure that we're okay with this. 2 to the -1 is 1 over 2 to the +1. 2 to the -2 is 1 over 2 to the +2, which is 1/4. 2 to the -3 is 1 over 2 to the +3, which is 1/8. So you need to be able to write that fraction, or write the common factor so it has a positive exponent, so we can work it out, right? And so we get a half, and then an eighth, or a fourth, and then an eighth, and then I guess it would be a 16th, and a 32nd, and a 64th. But there's a limit. Can I say that word? There's a limit on this. What's the limit?
0.
0. So that thing that you had on Alex the other day was asking about the asymptotes, right? In this case, guess what the asymptote is here? Now, yeah, 0, but it's a line. So it's the x-axis, right? Yeah, it's the x-axis right here is the asymptote, and its equation is simply y equals 0. So the asymptotes of all these exponential functions, they're always going to be horizontal lines. Okay, wherever that limit is, you know, where it's getting close to, but it's not hidden. So that's all you have to worry about. Now, the next one, y equals 5 times 2 to the x. So what changed here? What did this graph do? Say it louder. Did it slide up? Did it slide down? To the left? Okay, so we just end up right here. But this right here, how it goes over 1, up 1, over 1, up 1, and then over 1, up 1, 2, 3, 4, 5, 6. It's going to go over 1, up 6 again. It's going to have that exact same shape, isn't it? Okay, but this time, where's the asymptote going to be? Is it still 0? If it's going to have that same exact shape, just slide over to the left a little bit. I think it's going to have to look like that, isn't it?
But that would mean it had slid up.
That it what? That it slid up?
Yeah.
So let's take a look at our graph here. So when x is 0, what do we get? 5. So we get 1 times 5. When x is 1, what do we get? 10. When x is...
Would it be 6?
Well, hold on a minute. So when x is 2, then we get 4 times 5, which is 20. Okay, so is that keeping the same shape? Did it just slide left or right? Did it? Some of you did them on 4 different graphs. Some of you did them all on the same graph. So what do you think? Who did them on the same graph? Come on. Creek, raise your hand. Wake up. Who did them on the same graph? A few of you. Did yours just slide to the left or right, or did it actually take a different shape?
Mine just looking
Okay. So let's take a look here. One we got to go clear up to 10.
Teachers, would you send the softball team out to the little theater for the COVID testing?
When we get down here a little bit more, we put -1 in now. What's 2 to the -1 power? A half. And what's half of 5? 2.5. Okay, so can 4 be our asymptote? No, because we're coming down here to 2.5. Okay. If I put -2 in, this becomes 1 over 2 to the negative or positive 2, which is 1/4 of 5. 5/4, or 1 1/4. So now we're down here at -2. We're at 1 1/4. Where's this thing starting to turn? Put a -3 in. What do we get? 5/8. Okay, so that's close to a half, a little more than a half. Dang. What's going on with the asymptote again? Is it still 0? Yeah. Yeah, so we put it, if we put in a -4, this would be 5/16, which is about a third. And then 5 over 32, and then 5 over 64. So when it just slides to the left, does the asymptote change? So if it just slides to the right, is the asymptote going to change? No. So I have y equals 5 times 2 to the x. What if we put y equals 20 times 2 to the x? What's the asymptote still going to be?
0.
Still going to be 0. It's just going to slide to the left until that happens, right? Or what if we put a negative number there? We'll talk about that tomorrow. Okay, so now let's take a look at the next one there. Y equals 5 times 2 to the x plus 3. So we remember the y equals 5 times 2 to the x. It was 5, it was here 110, and then it was -1, 2.5, and then -2 was here and then here. So it has this kind of shape to it. So this is the y equals 5 times 2 to the x, right? So what's going to happen when I go plus 3? Okay, so now this is actually, it's literally going to slide up how many? 3. Is it going to keep the same shape? Yeah, it is. So instead of hitting 5, it's just going to hit 8, but it's going to keep that same exact shape. So what's going to happen to our asymptote though? And what's it going to be? Y equals 3. Y equals 3. Y equals 3. So if we think about that, y equals a times b to the x. Remember, this is our initial amount. That's going to be where it goes through, normally where it goes through the y-axis, right? This is our constant factor right here. When I just write y equals 2 to the x, I actually mean 1 times 2 to the x, don't I? We always have to think there's a number there, even if we're too lazy to write it. And then this deal over here, if I put like, right now, I suppose we're saying plus 0, and the asymptote's 0, right? But if we have a plus minus deal over here on the end, that's what's going to slide that graph up and down. That's what's going to change the asymptote from y equals 0 to something else, isn't it? Okay, is that helpful for the Alex thing where I was asking you about the asymptote? Okay. Can you see why knowing where that is going to help you graph that equation? Knowing where the asymptote is, that's something that we definitely want to think about. Okay. So, what do you guys remember about exponents? They do a lot of different things. I didn't teach you guys about exponents. Sometimes when I teach my algebra kids about exponents, sometimes we kind of think of them as our, you know, when you have a friend and they have a little brother or sister that always has to tag along with you, and they're always annoying, and they're always one step behind everything you're doing, and you're always having to tell them to hurry up, and okay. That's how exponents are to me. Exponents are always like, whatever you're doing, exponents are doing the thing right before that. Okay, so I'll give you an example. Let's say I'm adding. I have some like terms, I'm adding them together. What are the exponents doing here? Not doing anything. I'm adding, what are they doing? They're not doing anything. What if we're subtracting or adding a negative number? Are the exponents doing anything? No, they're just sitting there. They're not doing anything, are they? Okay. What about when you're multiplying? X squared times x to the third. So we're multiplying. What are the exponents doing? They're adding x to the fifth. And hopefully it makes sense. This is x times x. And this is x times x times x. And so there's literally 5 x's multiplied together here, aren't there? Okay. When we're dividing, x to the fifth divided by x to the third, what are the exponents doing? Yeah, they're subtracting. Just to remind you about something. X to the what? Think first. 5, subtract, -3.
Oh, that's 8.
8, yeah, okay. You remembered. Okay, and then when I'm raising something to a power, like I have x squared, and I raise it to a power. Okay, well, you look at that, and you kind of want to go 2 to the third is 8. Okay, but remember, are exponents ever doing what you're doing? No, they're always a step behind. This literally means x squared times x squared times x squared. And what do we do with the exponents when we multiply? We add them, right? So this is x to the 6th. So when we're raising something to a power, we don't raise the 2 to the third power, we just multiply the exponents together. And it doesn't matter if they're negative, they're still, the rules still apply. We're just multiplying those exponents together. So I don't know if that helps you remember anything about exponents or not, but hopefully it does. I think you've done some problems like this. Okay, so we can divide the c's. C to the 5th divided by c to the 1st. What does that give us? Okay, how come only one of you knows? 5 subtract 1. You with me? All right, let's keep going here. So then the d's, -2 subtract 5. Okay, and then the f's, 5 subtract 6. -1. Okay.
No, but then don't the D's and the F's have to be both?
They actually don't. So there's 2 different ways that we can write an answer, okay, like this, that are acceptable. One of them is all the variables are in the numerator, okay? Sometimes we hate fractions. I don't want to have to deal with fractions. I want all the variables in the numerator of the fraction, okay? Whether they have negative exponents or not, I don't care. I just want them in the numerator so I don't have to deal with fractions, okay? The other way is I hate negative exponents. I don't want to deal with them. And so if I move the d to the bottom of the fraction to the denominator and the f to the denominator, then I can write the answer with all positive exponents. And you'll be asked to do one or the other. If it doesn't say, then either should be acceptable. Either of these two answers is correct. So every variable in the numerator or everything written with a positive exponent. Okay? So just to kind of keep you going. Okay, so now enough reviewing. Let's talk about something new. Solving exponential equations. Like this one. 4 to the x equals 4 to the third. Can you guys tell me what x might have to be?
3.
No, doesn't this half the room know?
3.
What?
3.
Okay. Why? Because it makes the equation true, right? If I put a 3 here, wouldn't this be true? Okay, well that's the number then that x is equal to. So when we say x equals 3, we're saying if we put a 3 right there, then it will be equal, it will be true, right? So it's easy enough. How about this one? 2 to the x equals 2 to the 2x plus 4. What do you think? It might be a little harder to see in this case, but I'm going to propose something to you guys. 2 to whatever power this is and 2 to this power, if they're going to be equal, these two powers have got to be equal, don't they? So I'm going to say that x, this exponent here, has got to equal 2x plus 4. Can we solve that? Yeah? Subtract 2x from both sides. Divide both sides by -1. So if x were a -4, 2 times -4, that's -8, plus 4, I'd get 2 to the -4 equals 2 to the -4. Are they equal? Okay, so notice what I'm doing then? I'm setting the exponents equal to each other and then solving that part of it. So all easy. Okay, so now
We just have to multiply 5x plus 1 by 2 because 2 to the power of 2 equals 4. So that would be those two.
So do you guys see our problem then? What we're talking about here? And Tyler's trying to adjust for that, isn't he? Right? Okay, so we don't have the same base. We don't have the same base. So this x is not going to equal 5x plus 1, is it? Because we don't have the same bases. So the way you were looking at it, like adjusting the exponent, yes. And we are going to do that, but I think, can we write them so the bases are the same? So I know that I can write 4 as 2 to some power. Can't I? So is 4 the same thing as 2 to the second power?
Yeah.
And that's already being raised to what? The x power. And what do you do with these exponents when you raise them to a power like that? We multiply them, don't we? Okay. So this is the same thing as 2 to the 2x power. Now can we solve this?
Yeah.
Now it's easy, isn't it? Once we have the bases the same, then we know that 2x has to equal 5x plus 1, and we can solve that and find x, hopefully fairly simply. Wait a minute, can an exponent be a fraction?
Yeah.
Yeah. Can it be a decimal?
Yeah.
Yeah. It can be about anything. So, okay, so I think what we need to practice the most is thinking about, can we write things so that they have the same exponent? So let's say I have 9 to the blah 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 power, doesn't matter, and I have I don't know, 81 to some power. Can I get these bases to be the same thing?
Yes.
Right? So what are you guys thinking?
You could,
Hold on. What are you guys thinking?
You could change 81 to 9 squared.
Okay, so we could change 81 to 9 squared. So we'd have 9 squared, and then we'd multiply that by whatever it was, whatever the exponent was before, right? And over here we'd have 9. Could we solve it then? Okay. Or, how about this? Could I say 9 is 3 squared to the blah blah blah, and 81 is 3 to the 4th power? Could I write them both that way?
yeah.
We could. And you know what? We kind of like to break them down to the simplest base that we can. Okay? Rather than saying 9 to some power. But you know what? If all you got to do is solve for x, not a big deal. What about this?
You could change the bases to 2 by multiplying each exponent by 2.
Wait, I could change the 1/8 to what?
2.
I think that's 2 steps.
Well, you could just do it, multiply that exponent by -3, right?
Yeah, but you're still doing 2 steps. I'm going to slow it down. I'm going to slow down and do 1 step. Do you guys like this to be a fraction and this to be a whole number? Is there a way I can write that so it's not an eighth, so I could write it 8 to some power? Does 1/8 equal 8 over 1 to some exponent?
Yeah.
What exponent is it?
-1, yeah.
-1. So I'm just going to throw this out there. 2/3 to the -1 is 3 over 2 to the... It's kind of the reciprocal, isn't it? Isn't raising something to the -1 power doing the reciprocal? Okay. So right here, I can change that to 8 as long as I raise it to the what power? -1, which means this exponent would have to be multiplied by, what does that give me? -2x subtract 4. Subtract 4? You going to use the distributive property? Okay, and then on the other side we've got 16 to the 4 minus x. Okay, now can I write them with the same bases? What base are we looking at? 8? 4?
2.
I'm gonna go down to 2. I don't think I can write 8 as 4 to a power very easily. Do you guys? Can we write 16 as 8 to a power? No, it's 8 times 2, but it's not 8 to an exponential power very easy, is it? But can we write 8 as a 2? 2 to what power?
3.
The 3rd power, which would have to be multiplied by the exponent we already have. What about 16? 2 to the 4th power, which would also have to be multiplied by the exponent that's already there. Okay, can we solve and find x now? Ooh. Good times? Will? Your brow is furrowed.
Yeah.
Let's look at another.
They're ready for the baseball team over in the little theater. Baseball team, go to the little theater.
1/9 and 27. Can you guys just get these two numbers to be written as the same base to an exponent?
Yeah.
Just do it on that paper you had. And I do it as 2 steps. Like, first of all, I don't like the fraction thing. Let's take care of that, and then let's worry about changing the base part. you still have negative 1 right there. Rest. That's to carry on. Okay, I showed every little step, okay, and I probably shouldn't have put the equal sign here. But first of all, I thought about, okay, I don't want it to be written as the fraction, I want it to be written as a 9, so 9 to the negative 1, which is 3 squared, still raised to the negative 1, which is 3 to the negative 2, which does not equal 3 to the third. Sorry, I shouldn't have put that there. But in your problems, you're going to have something like, this is raised to the x plus 2, this is raised to the 2x plus 3, and so you're still going to have x plus 2 here, and 2x plus 3 here, and then times x plus 2 here, and times 2x plus 3 here. And so we're going to end up with negative 2x, subtract 4, and this would be 6x plus 9. And so in this case, now can we solve and find the variable? Okay. Do you see why it's a good idea to write it at least this way first? All right. Well, all right, we've talked about it, we've practiced it. Now it's time for you guys to practice on your own. Ready for this? This daylight savings time, boy, you guys look like you are loving it.